Okay, this is the last video in the series of 3 videos looking at uses of the Maclaurin series. We'll do 2 examples here, one where we'll use this list of 7 to be able to integrate a function that we can integrate. There's no closed form way of figuring out, no special technique, and in that case then we can sort of resort to just finding the Taylor series and replacing the function with the Taylor series. After that, what we'll do is talk about how if we don't have one of these 7, and maybe if we're not centered at a equals 0, the Maclaurin series is a Taylor series where we have centered at a equals 0. And so we'll look at, well, what if we want to center someplace else? Maybe it's one of these 7, maybe it's not one of these 7. What do we do then? And so that's what these 2 videos are about. First up is you want to be able to use a power series to integrate a function when there doesn't seem to be an apparent integration technique that we could use. X cubed e to the negative x cubed. And so we want to be able to integrate that, but there's no u substitution, no straightforward way, at least, for us to find this antiderivative. So instead, we are going to build up the power series for this function, replace that function with the power series, and then we'll be integrating the power series. We can do it term by term, or we can do it with the summation form, whatever it might take. Now remember, e to the x is the series where we have x to the n over n factorial. Now if we have e to the negative x, what that's going to have is basically the same guy but alternating. Okay, well we don't have that. We have e to the negative x cubed. So ultimately what we're doing is replacing x, taking e to the x's power series here, and replacing x with negative x cubed. I try to do it in 2 steps. Let's just do it in 1 step. So e to the x's power series is x to the n over n factorial. And so what we're going to do is replace every x with negative x cubed, and we have the power series for e to the negative x cubed. And then from that, we're not done yet. There's still an x cubed here. And we could split this up. It doesn't have to be this written in this manner. We could split it up where we have negative x cubed being a negative 1 times an x cubed. And then if that's all raised to the n, then we can raise each one of these to the n. And that's what's happening here and here. The whole thing is raised to the n. And so then we can raise each one to the n. So this is the power series for e to the negative x cubed. Great. Now from that, what we're going to do is multiply it by x cubed. So we have this summation, and we're going to multiply it by x cubed. What we're going to do is incorporate that on the inside here. We're going to put the x cubed on the inside, and then simplify the exponent on x. If I have x to the 3n, and it's multiplied by x to the 3, with those exponents, I add them together. And so what we found is a power series representation for x cubed e to the negative x. Now we want to integrate this. The integral of a power series would be us basically integrating this symbol here. And to do that, what we're going to do is realize that the integral of a sum is the sum of the integrals. So what's going to happen with these 2 operations is they're going to interchange. We're going to bring the integration on the inside. And then another step that I've done here is, you don't have to do this, but this is just a constant, the alternating part and the n factorial. It's constant. Our integral is on x, and so what we can do is pull that out, focus on this integral on x, integrate there with the power rule, and then we'll have it back inside of the summation. So x to the 3n plus 3, we have to find the antiderivative by adding 1 and dividing by the same thing, so we get 3n plus the 4 now as our new exponent, divided by 3n plus 4, the negative 1 to the n factorial. And there's really infinitely many of these plus c's. This is an indefinite integral. And so we can put that part first. So we don't know what this guy is. We don't know the formula for this. Call it g of x. There's some function out there who has x cubed, either negative x cubed as its derivative. And what we just found was that particular function's power series representation. We did it with summation form. We could have done it with the first few terms. Most questions just say, use the first 4 terms and do it. But here it's done with summation form. Find the power series of something that you don't have a power series for by using the 7 that are on the list and the execution of integrating that power series. Okay, great. Now, what if you want to find the power series for a function that's not on that list and also not centered at x equals 0? When you're centered at 0, you have a Maclaurin series. When you're not, then you just have a generic Taylor series, and it has a certain way of and so a Taylor series will look like some constant and then some constant c1 times x minus a to the first power, c2 times x minus a to the second power, and so on. We could keep going, but this particular question said second order Taylor series. Second order, so that doesn't mean second term. What that means is if you're going to be a second order Taylor series, that takes you up to the x squared term and no higher terms on x. And so we would stop right here. The symbol for it is called T2, and it's the second order Taylor polynomial, and it's quadratic. It's a quadratic. In fact, this is a way to approximate the function. Back in Calc 1, you used this first part and you called that the tangent line. And now if you want a higher order approximation, we just add more terms to the Taylor series. So this particular one is called a quadratic approximation. And so we're stopping. That's why we don't have a full equals to. We have this symbol here, and that symbol means that it is approximately equal to. We've chopped off infinitely many terms. We won't get the accuracy, but we at least can still use this and be able to do something with it. And so we have to basically start from scratch, in essence. Okay, we don't have the use of the list of 7 Maclaurin series, and so we just go with the way we develop those guys by taking the function. These guys have a special format to them. These coefficients are the nth derivative at a, all divided by n factorial. And what we had done was we did these in 3 different parts. We first go find the n derivatives, and then we go, in this case, plug 8 in, and then we divide that by n factorial in a systematic manner. So that's what we're going to do here. We're going to first start off with the function itself. That's the 0th derivative. And then we take the first derivative, and we take the second derivative. We know to stop there because we're trying to take it up to x squared, and so we stop at the n equals 2 level. And this thing starts at n equals 0. The next step in the process is, now that you have these derivatives, this numerator is you taking these derivatives and plugging in a, and for us, the center is a. That's called 8. So we plug an 8 in. That's 8 to the 1/3 power. That's just the cube root of 8. So it's a 2. Great. We then move to the derivative. We plug an 8 into that. So what I quickly glossed over here is these derivatives, just power rule. You bring down the exponent and take away 1 from it. At this second level here, you already have a 1/3 down, and you bring a negative 2/3 down. And so we have a negative 2/9 down, and take away 1 again. So these are my derivatives, and my job is to plug in 8 to these guys. Now this is going to be a little bit difficult algebraically, but the negative exponent puts it to the denominator, and so we're talking about 1/3 times 8 to the 2/3. The way you handle 8 to the 2/3 is you make it 8 to the 1/3 since it's a perfect cube, and you then square that. When you raise to a power to another power, that's like multiplying the exponents. Well, we know that 8 to the 1/3 is 2, so then 2 squared would be 4. So replacing 8 to the 2/3 would be a 4. And so this guy is just 1/12. And then finally we have our second derivative at 8, which is negative 2 over 9, 8 to the 5/3. Same way we did the other one, we're going to take it to the 1/3 and then take it to the 5th, because we're going to have a 2. The cube root of 8 is a 2, and that 2 to the 5th is 32. And so we replace 8 to the 5/3 with 32. We can do some canceling. This can turn into a 1 and turn 16 for the 32. 16 times 9 is 144. And so what we've done is found the coefficients numerators. We've taken the nth derivative at A for each of the ones we need. We needed C0, C1, and C2. We're trying to find these guys. And we've done the first part, but we have to remember that we haven't done the second part, which is dividing by n factorial. N is the level that you're at. 0 factorial is defined to be 1. By definition, 0 factorial is 1, and 1 factorial is 1. 2 factorial is just a 2. And so we take these numbers here and divide them by 1 for 2. 2 divided by 1 is 2. 1/12 divided by 1 is 1/12. And negative 1 over 44 divided by 2 is negative 1 over 288. And we did it. We found our coefficients. Now we have exactly the C sub n's. We have C sub 0, C sub 1, and C sub 2. Our job is to put them into this polynomial, and then we're done. And so we have 2. It is the 1/12 that gets multiplied by x minus 8, and is the negative 1 over 288 that gets multiplied by x minus 8 squared. And so we have done it. We have found the second order Taylor series for the cube root of x, and at 8 is where it's centered at. And so the function y equals the cube root of x has a sort of flow to it. And what we just did is we went and fit a quadratic function centered at 8. We fit a quadratic function, and it's going to look a lot like our function as long as we're nearby 8, but at some point it's going to bend and not be a very good approximation. And so T2 is this polynomial that we went and found. It's a parabola. It's a quadratic approximation. All right, and that is it. That is the end of the applications to Taylor and Maclaurin series. Thank you.